Hello everyone, I am Aanchal from BSc Chemistry Honors Final Year. Today we will discuss vibrational spectroscopy. Vibrational energy level of a simple harmonic oscillator. A simple harmonic oscillator is the one in which the restoring force is proportional to the displacement in accordance with Hooke's law, that is F is equal to minus kx, where k is called force constant. For such an oscillator, the potential energy is given by is equal to half kx ka square, equation 2. This is the equation for a parabola. Hence, a parabolic potential energy curve is obtained as shown in figure 3.21. Using the concept of quantum mechanics, it can be seen that if the vibratory motion of the nuclei of a diatomic molecule is taken as equivalent to that of a simple harmonic oscillator, then the vibrational energy is given by the equation Ev is equal to V plus half into h nu, where nu is the frequency of vibration and nu is the vibrational quantum number with allowed value of 0, 1, 2, 3, etc. Putting V is equal to C upon lambda is equal to C V bar E, where V bar E and omega E represents the equilibrium vibrational frequency in terms of wave number. Equation 3 can be written as EV is equal to V plus half into HC omega E. Putting mu is equal to 0, 1, 2, 3, etc. in equation 4, it may be seen that the vibrational energy levels of a harmonic oscillator are equally spaced. These are shown diagrammatically in figure 3.23. For the lowest vibrational level V is equal to 0, the energy for this level will therefore be E naught is equal to half HC omega E. This is called 0 point energy. It implies that even at absolute zero, when all translational and rotational motion ceases in a crystal, the residual energy of vibration E naught still remains, that is, the vibrational motion still exists. Selection rule for the vibrational transitions in a simple harmonic oscillator. The gross selection rule for a molecular vibration is that the electric dipole moment must change when the atom are displaced. Here note that the molecule need not have a permanent dipole. Based on this, the specific selection rule for vibrational transition is for a diatomic molecule X is equal to R minus Re, where R is distance to which the atoms have been stretched and Re is the equilibrium distance between the two atoms. Mu bar is avoided because this is used to represent the frequency of the spectral line. Delta V is equal to plus minus 1, that is change in vibrational quantum number should be unity. Transition for which delta V is equal to plus minus 1 correspond to absorption, and those with delta V is equal to minus 1 correspond to emission. Vibrational spectra of a simple harmonic oscillator. Applying the selection rule, as the transition can take place between vibrational level whose vibrational quantum numbers differ by unity, that is delta V is equal to plus minus 1, the energy absorbed by a diatomic molecule taking it as a simple harmonic oscillator when the transition takes place from V to V plus 1 level will be given by delta E V is equal to V plus 1 plus half into HC omega E minus V plus half HC omega E is equal to HC omega E, or delta E upon HC is equal to omega E, that is delta V bar is equal to omega E. Thus only one absorption line will be obtained in the vibrational spectrum whose wave number is equal to the equilibrium vibrational frequency of the diatomic molecule. Otherwise too, as the vibrational level are equally spaced, any transition from any V to V plus 1 will give rise to the same energy change, and hence only one absorption line is expected. Further, at room temperature, as most of the molecule are in the lowest ground state vibrational level with V is equal to 0, with therefore the transition take place are from V is equal to 0 to V is equal to 1. The frequency thus observed is called the fundamental frequency. These spectra are observed in the infrared region. Type of molecule showing vibrational spectra. As already mentioned, the gross selection rule for a diatomic molecule to give a vibrational spectrum is that the dipole moment of the molecule must change when the atom are displaced due to vibration. so that it can set the electromagnetic field into oscillation. The condition required is only the change in dipole moment, possibly from zero, and the molecule need not have a permanent dipole moment. For example, in case of homonuclear diatomic molecules like H2O2, N2, etc., which have only stretching motion या vibration and no bending motion या vibrations, the dipole moment does not change during vibration. Hence these molecules do not give vibrational spectra, that is, they are said to be infrared inactive. On the other hand, heteronuclear diatomic molecule like HCl, CuNO, etc., are polyatomic molecules like CO2, H2O, CH4, C2H4, etc., which show change in dipole moment in some mode of vibration, give vibrational spectra, and are said to be infrared active. Vibrational energy levels of an enharmonic oscillator. When a molecule is undergoing simple harmonic oscillations, the restoring force of the harmonic vibrations is directly proportional to the displacement, and the energy of the harmonic oscillator is given by EV is equal to V plus half into Hc omega E, where V is the vibrational quantum number, which may be 0 or an integer, and omega is the equilibrium frequency of vibration of the oscillator, that is, for small displacements. Strictly speaking, the movement of a real oscillator is not perfectly harmonic. This is because as the displacement increases, the restoring force becomes weaker, and for large enough amplitude of vibration, the atoms of the molecule must fall apart. That is, the molecule must dissociate into atoms. Such a real oscillator is said to be an harmonic oscillator. PM Morse in 1929 suggested that the above equation has to be modified for an enharmonic oscillator by including one additional term as follow: EV is equal to V plus half into Hc omega E minus V plus half whole square Hc omega E, equation 2, where Xc is called the enharmonicity constant. Putting V is equal to 0, 1, 2 in equation 1 and 2, the energy levels of the harmonic oscillator and the enharmonic oscillator may be obtained. It may be seen that whereas the energy levels of a harmonic oscillator are equally spaced, those of the enharmonic oscillator are not equally spaced but fall more closely together as the quantum number increases whether further, whereas the potential energy curve for harmonic oscillator is a parabola. Figure 3.24a. That of the enharmonic oscillator is as shown in figure 3.24b. Selection rule for the vibrational transition of an enharmonic oscillator, whereas the selection rule for the harmonic oscillator is delta V is equal to plus minus 1. The selection rule for the enharmonic oscillator are delta V is equal to plus minus 1, plus minus 2, plus minus 3, and so on. Thus all type of vibrational transitions are possible. However, the transition from V is equal to 0 to V is equal to 1 is found to be most intense due to greater population of this energy level and is called the fundamental absorption. The transition from V is equal to 0 to V is equal to has a very weak intensity and is called the first overtone. The transition from V is equal to 0 to V is equal to 3 has still weaker intensity and is called the second overtone, and so on. Vibrational rotational spectra. Pure vibrational spectra are obtained only for liquid where rotational motion is hindered due to interaction between the liquid molecule. However, in case of gaseous molecule, as the energy required for rotation is much less than that required for vibration, the vibrational motion is always accompanied by rotational motion, and hence we do not have a pure vibrational spectra. Instead, we have a vibrational rotational spectra lying in the infrared region, as rotational motion and vibrational motion take place independent of each other. Applying Born Oppenheimer approximation, the total energy of the molecule may be taken as the sum of the rotational energy and the vibrational energy, which is much larger than the former. Thus, E total is equal to ER plus EV, or it can be written as EV comma J is equal to EJ plus EV. Expressing in term of wave number, it can be written as V bar V comma j is equal to v bar j plus v bar v, but from equation 4 v bar j is equal to bj into j plus 1, v bar v is equal to v plus half into omega e minus v plus half whole square xc omega e. Substituting this value in equation 15, we get v bar v comma j is equal to bj into j plus 1 plus v plus half into omega e minus v plus half whole square xc omega e. Here v bar v comma j represent the wave number of a rotational level with quantum number j in the vibrational level with quantum number v. From equation 6 it is clear that in the same vibrational level, so that v is equal to constant, there will be a number of rotational level corresponding to j is equal to 0 1 2 3 when a transition take place from a level with quantum number v and j to a level with quantum number v dash and j dash. The energy change expressed in term of wave number will be given by delta v bar is equal to b j dash into j dash plus 1 plus v dash plus half into omega e minus v dash plus half whole square xc omega e. Restricting to the transition from v is equal to 0 to v dash is equal to 1, we get b j dash into j dash plus 1 plus 3 by 2 omega e minus 9 by 4 xc omega e minus b j into j plus 1 plus half omega e minus 1 by 4 xe omega e is equal to b into j dash plus 1 minus j into j plus 1 plus omega e minus 2 xe omega e is equal to b j into j dash minus j into j plus j dash plus 1 plus 1 minus 2 xe into omega e. Putting 1 minus 2 xe omega e is equal to omega 0, we can write delta v bar is equal to omega 0 plus b into j dash minus j into j plus j dash plus 1. First, for transition with delta j is equal to plus 1, that is j dash minus j is equal to plus 1 or j dash is equal to j plus 1. Delta v bar is equal to omega 0 plus 2b into j plus 1, where j is equal to 0 1 2 3. Second, for transition with delta j is equal to minus 1, that is j dash minus j is equal to minus 1 or j is equal to j dash plus 1. Delta v bar is equal to omega 0 minus 2b into j dash plus 1, where j dash is equal to 0 1 2 3. Combining equation 10 and 11, we get delta v bar is equal to omega 0 plus 2bm, where m is equal to j plus 1 in equation 10 and m is equal to minus j into j dash plus 1 in equation 11, as j is equal to 0 1 2 3. This means that in equation 12 m is equal to plus minus 1 plus minus 2 plus minus 3. Positive sign for delta j is equal to plus 1 and negative sign for delta j is equal to minus 1. The nature of the vibrational rotational spectrum can be predicted from equation 12 as follow. First, as m not equal to 0, therefore line corresponding to the frequency omega 0 will not appear in the spectrum. This wave number is called the band center or band origin. Second, as m is equal to plus minus 1 plus minus 2 plus minus 3, it follow that the spectrum will consist of equally spaced line on each side of the band center with spacing equal to 2b between any two adjacent lines. Keeping in view the selection rule delta j is equal to plus minus 1, the absorption transition that can take place from level v is equal to 0 to v is equal to 1 and the corresponding line obtained in the spectrum may be represented as shown in figure 3.25 on the next page. P, Q and R branch of the vibrational rotational spectra. In equation 2, omega 0 represent the fundamental frequency. This is called the center of or origin of the fundamental band. For delta j is equal to minus 1, lines with frequency lower than the fundamental frequency are obtained. These lines are called the P branch of the spectrum. For delta j is equal to plus 1, line with frequency greater than the fundamental frequency are obtained. These lines are called the R branch of the spectrum. For delta j is equal to 0, that is when a vibrational transition occurs without accompanied by rotational transition delta V bar is equal to omega 0, that is a single line should be obtained at the center. In actual practice, as the rotational constant of the two vibrational level are slightly different, a cluster of closely spaced lines appear at the center. This group of line is called the Q branch of the spectrum. When this type of transition is forbidden, example in case of HCl, a gap appear at the center. Intensity of the lines in P and R branches. It is important to note that intensity of the lines in P and R branch of the type shown in figure 3.25b will be observed only if the resolving power of the spectrometer is very high. If the resolving power is not so high, then the spectrum observed is as shown in figure 3.26. Structural information from infrared spectra. By carefully locating the band center corresponding to the transition V is equal to 0 to V dash is equal to 1 fundamental transition, and the transition V is equal to 0 to V dash is equal to 2 first overtone, the value of the frequency omega E and the harmonicity constant xe can be obtained. Also, the frequency separation between any two adjacent lines of the P branch or R branch give the value of 2b. Knowing the value of omega e and xe, the force constant and dissociation energy of the molecule can be calculating, and knowing the value of b, the moment of inertia and bond length of the diatomic molecule can be calculated as explained below. First, calculation of moment of inertia and bond length. As discussed in the rotational spectra, B is equal to H upon 8 pi square IC. Frequency separation delta V bar is equal to 2B is equal to H upon 4 pi square IC. Thus, knowing the frequency separation, the moment of inertia, and hence the internuclear distance, that is bond length of a diatomic molecule, can be calculated. Second, calculation of force constant. Taking the simple case where a diatomic molecule may be considered as a simple harmonic oscillator, that is an oscillator in which the restoring force is directly proportional to the displacement. In accordance with Hooke's law, we have F is equal to minus kx, where x is the displacement and is equal to the distance to which the atoms have been stretched, r minus equilibrium distance between the atoms re, that is x is equal to r minus re, in equation 13 is called force constant. Thus, if x is equal to 1 centimeter, k is equal to minus f. Hence, force constant may be defined as the restoring force per unit displacement or per centimeter of a harmonic oscillator. It is found to be related to the equilibrium vibrational frequency omega e. According to equation, omega e is equal to 1 by 2 pi into k upon mu whole half, where mu is the reduced mass of the system. To calculate k, equation 14 can be rewritten as k is equal to 4 pi square omega e square mu. K is equal to 4 pi square omega e square into m1 m2 upon m1 plus m2, where m1 and m2 are the masses of the oscillating atoms. Thus, knowing vibrational frequency omega e and the masses of the atoms of the diatomic molecule, the force constant k can be calculated. Now that omega is in second inverse, however, a problem arises with the polyatomic molecules because each bond has a different force constant. This problem is solved by assuming that a force constant is associated not only with every bond but also with every bond angle. A detailed study of such molecule is beyond the scope of the present book. The force constant for a number of books have been determined. It is found that force constant increase almost directly with the multiplicity of the bond. This is illustrated by some values given below. Bond is equal to force constant. Carbon single bond carbon 4.6 into 10 raised to power 5, carbon double bond carbon 9.5 into 10 raised to power 5, carbon triple bond carbon 15.8 into 10 raised to power 5. Thus, the multiplicity of the bond can be predicted from the value of the force constant. For example, the force constant for carbon triple bond O in carbon monoxide is 18.6 into 10 raised to power 5 dyne per centimeter, whereas the force constant for carbon double bond O in carbon dioxide is 15.2 into 10 raised to power 5 dyne per centimeter. This result confirmed that CO2 has resonating structure containing both carbon oxygen double and triple bonds, that is we can write Thank you.